Okay, so this video we're going to talk about section 5.5. 5.5 is the Fibonacci sequence and the golden ratio. So way back in chapter 1, we talked about inductive reasoning, and then we talked about sequences. So I'm going to start writing down a sequence here, and this sequence is called the Fibonacci sequence. You might already know what's going on with the sequence, but we'll just start here. 1, 1, 2, 3, 5. So remember in chapter 1 you were asked to find the next term of the sequence, and we had some tricks. Like remember we had arithmetic, where you keep adding the same number repeatedly. Well, that doesn't work here. 1 plus 0 is 1. What the second 1 plus 0 is not 2. So that's gone. Geometric, when you multiply the same number repeatedly, 1 times 1 is 1, but the second 1 times 1 is not 2. So it's not geometric. We had successive differences. Successive differences won't work either. Not the way you think it would work, I should say. So with that, we sort of have to think outside the box and say, okay, what else could generate this sequence? Remember, there are some sequences that don't have a known pattern. This one does still. Notice that 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. So what's 3 plus 5? 8. And then what comes next? 5 plus 8, 13. And then 8 plus 13, 21. And I could just keep going here. 34, 55, 89, ... Alright, so this is the very famous sequence, the Fibonacci sequence. Fibonacci, also known as Leonardo di Pisa. Fibonacci was his nickname. He is sort of credited with bringing the Hindu Arabic numbers to the West. So at that time, people were basically just using Roman numbers in Western Europe, and Fibonacci supposedly learned about the Hindu Arabic numbers from some of the travelers there. Hindu Arabic numbers, you may have never seen these before, but they look like this. I skipped a number there, didn't I? 7. It's not that important. Everybody knows this. Yeah, these guys are called your Hindu Arabic numbers. That's the symbols we use. Or depends on who you talk to. You might just hear them as the Hindu numbers or the Arabic numbers. But the book calls them Hindu Arabic, so that's what we're going to go with. So he found out that you can do all sorts of mathematics with these 10 symbols that you couldn't easily do with Roman symbols or with other cultures, Mayan or Babylonian or Chinese. The Hindu Arabic were much, much better for very small and very big numbers. If you want, this was one of the movies we're going to watch. It's called The Story of One. You can watch it on YouTube if you like. It's an hour long. It'll pass the time if you're bored in your house, and you can learn about some math there. Very, very nerdy good stuff. So there's that. Okay, so these numbers might seem very, very random, and in fact, the way they came about was very, very random. Fibonacci was like, hey, let's suppose I had a mating pair of rabbits, and the rule is they're allowed to have one offspring each cycle, and then that offspring can grow and then become part of another mating pair. Okay, so that's where the Fibonacci sequence comes from. Rabbits. Now, with that said, it still is a very, very interesting sequence. Like, for instance, there's a lot of math that comes out of it. I really don't have these in any certain order, so let's just play with the numbers themselves first. In your homework, you'll learn how the Fibonacci sequence can generate a Pythagorean triple. So we talked about Pythagoras earlier on in this chapter, and remember we had a squared plus b squared equals c squared is the Pythagorean theorem. For instance, 3 squared plus 4 squared is 5 squared. And 6 squared plus 8 squared is 10 squared. So there are triples, 3, 4, 5, 6, 8, 10, for example, that will satisfy this equation a squared plus b squared equals c squared. So in your homework, you learn how to take a string of 4 numbers in the Fibonacci sequence, and you do 3 things to them, and that tells you an A, a B, and a C. And it'll always work. So that's one thing that the Fibonacci sequence can do. It can generate answers to the equation a squared plus b squared equals c squared. As far as less abstract things that you could use the Fibonacci numbers for is many flowers will have petals that are described that will be the number of Fibonacci a number in the Fibonacci sequence. Now actually there isn't there a lily? I think there's a lily that has only 1 petal, so there's that one there. I don't know one offhand of 2 or 3. And I really don't know my flowers very well. I need to play Animal Crossing some more, is what I'm trying to tell you. So you might have flowers that will have petals with a Fibonacci number. More hands-on would be a pineapple. I know, I said it. Let me look up pineapple Fibonacci. Believe it or not. Oh, this wonderful person. So, you know what? These are fine. I'll just bring the screen over. So, on a pineapple, if you've never noticed, there's 2 types of spirals, technically. You have spirals going diagonally down to the right, and you have spirals going diagonally down to the left. If you were to count these spirals, they will be a Fibonacci number. Namely, I think it's typically 8 and 13, if I remember correctly. So someone had made the pins here. They really had a lot of time here. And notice in this one, you see the clockwise and the counterclockwise spirals. So spirals in a pineapple will be a Fibonacci number. That's also true. I let the cat out of the bag. There's no cat here. For pine cones. And it's also true for sunflowers. So here's a really good one here. Someone nerdily counted the spirals. So same deal, you have clockwise and counterclockwise spirals. If you look at a sunflower, how that burst in the center there, those seeds, I think those are also Fibonacci numbers, probably to the higher end, maybe like 55, 89 kind of deal. So in nature, there's a lot of good examples of seeing the Fibonacci sequence. Nerd, good stuff. Okay, now there's this other thing that it's related to called the golden ratio. So the Greeks were like, hey, look at this rectangle. I'm not going to draw it correctly, and I do apologize. I mean, that rectangle is a great rectangle, and it's pleasing to the eye. And there's a mathematical reason. It's because the length of this side divided by the length of this side gives you this number, and that number is called the golden ratio. It's approximately, as a decimal, 1.518, I think. I have it written down. Oh no, 1.618. I apologize. 1.618. 18. Boop. And the reason it's so cool is because now if you watch the other movie, Donald Duck in Mathmagicland, if you take this side and flatten it down, and wherever it lands, make it go up, then this portion here, divided into this portion here, gives you the same number, 1.618. And then if you did the same thing, make this side... I don't know where my cursor is ever in this program. Make this side flatten up to here and go over here. This side divided by this side, I think it is. I'm getting confused. This drawing is getting too intense. It gives you the same number, 1.61828. As far as how the Fibonacci sequence and the golden ratio are related is if you took two numbers in this Fibonacci sequence that are next to each other and divided the biggest by the smallest, you get closer and closer to 1.618. So for instance, 5/3 is 1.6 even, 8/5. Let me get some, I need to get my calculator in here. That's not my calculator. Sorry, my phone's going off there and I did not answer it. 5 divided by 8. I'm sorry, 8 divided by 5 is, oh, that's 1.6. 13 divided by 8 is 1.625. 21 divided by 13 is 1.61538. 34 divided by 21, 1.61905. So if you looked at the sequence of numbers, you keep bouncing around this 1.618. And if you kept going higher and higher and higher, you get closer and closer. So that's the link between the Fibonacci sequence and the golden ratio. Now, how is the golden ratio important? Well, we can talk about a bunch of things. We can go back to nature again. If you think about how a plant forms, when a plant grows its leaves, and I'm going to pause right here. Sorry about that. Okay, so let's suppose we had a leaf on a plant. Do you think it's in the plant's best interest to grow the leaves so that they are right on top of each other? So if you were looking at the plant down and the stem could grow vertically straight, do you think it makes sense that the leaves are right on top of each other? Hopefully you're saying no, because the purpose of the leaves is to collect sun. And if they're right on top of each other, then the leaves on the bottom can't collect as much sun as the leaves above it. All right, so let's suppose instead of like a 90 degree, it was like a 20 degree turn. Okay, well, a 20 degree turn may be closer to this. That's cool, but then what's going to happen is eventually they're going to stack again. So yeah, you get more leaves in the sun, but the lower leaves serve no function. So what does a plant do? Well, as it turns out, the ratio between where the leaves are for a plant is approximately this number, 1.618. Because this number is irrational, meaning no matter how many stacks you have, there will still be a little portion of lower leaves sticking out from the bottom, getting some sun. So all the leaves will be functional at that point. So it's better if a plant used an irrational number, 1.618 for example, than a rational number like 90 degrees or 20 degrees or things like that. What's also cool is if you think about how a tree grows. Boop, that's my tree, it's pretty, thanks. If you thought about the branches themselves, these branches are larger, they stick out further out, right? Again, the purpose is to get more sun from the leaves. And then the next ones aren't as, they get closer and closer as you go to the top. And the reason is because, again, you're sort of seeing the golden ratio into play. This box here can form this box here, can form this box here. I'm not doing a really great job of illustrating it, so I would recommend watching like the middle portion of Donald Duck and Magic Land. You can find this on YouTube for free, so highly recommend that. So there are some natural reasons to where the golden ratio comes into play. Also, like if you looked at seashells, the shell itself, that's called a golden spiral. That also would fit inside this rectangle here. And one other really cool thing is the human face, for example. Boop, boop, bink. Not a good human face, not the point. But if you took the length of the head, so the top of the head to the chin, that number, and took the length from the eyes to the chin, and you divided those two numbers, you get approximately 1.618. If you took the, I think it would be, I don't want to go back to the face because I don't remember everything for the face. If you took the body Here's the feet. If you took the whole body from the top of the head to the feet and divided it by where the belly button is, down, you get approximately 1.618. If you took the arm and divided it from the fingertips to the elbow, those two numbers, you get approximately 1.618. So on and so forth. Even like the way your bone, so like from here to, so this ratio here compared to this ratio here, I think that's another golden ratio going on there. So the way even that your fingers are formed can be approximated by the golden ratio. So really, really cool things. And then, well, nerdy cool, if anything. The project that you were going to have for this section was the mathematics of beauty. Do we declare in our own minds, do we declare someone to be beautiful based on the proportions of the face? Meaning, if a person's face is closer to this golden ratio, do we think that they're more attractive? Things like that. But we're not going to do that project anymore. You can read all about that online if you so choose. All right, that is 5-5. Unfortunately, there's no examples, really. It's just playing with numbers. So when you're doing the homework problems, and yes, there are homework problems, just follow the directions. They tell you step by step what you need to do. And if, as always, ask me if you have questions. Now, with that said, that concludes Chapter 5. We're not doing Chapter 9. So, when I forgot what date I had set out in the emails, whenever that occurs, I will open up back all of the homework so you can catch up on whatever you had missed from Chapter 1. So your final is basically only covering 1 through 5. We're not having 9 on the final. Okay. Let me know if you have questions. Have a good day. Click.